Hey everyone, welcome back to TechOps tutorial. In today's session, we are diving into an essential topic for both system administrator and a developer, that is Kubernetes networking. Whether you are wondering how pods communicate, how services discover each other, or how to manage external access and a security, this video will cover everything. We will break it down step by step, covering pod, services, DNS, CNI plugins, and network security with real-world context and example. Let's start with a simple question. Why does networking matter so much in Kubernetes? It's not just about connecting the containers. It's about creating secure, stable, and scalable communication. Whether you are a developer deploying microservices or a system administrator managing the workloads, networking is a key for debugging, scaling, and security. Now let's make this easier to visualize. Think of a Kubernetes cluster is a city. Each pod is like a house. Each service is a road connecting those houses. And the external user, they are the visitor from outside the city trying to find the right house. Kubernetes takes care of all the infrastructure and traffic control, building the roads, assigning direction, and keeping everything flowing, so your app can communicate smoothly and efficiently. This networking layer is what makes your application truly production ready. Kubernetes networking is built on 4 key goals, and together they create a seamless, efficient network architecture. First, every pod gets its own IP. That means each pod can talk directly to other without needing complex port mapping. No NAT required, just clean and direct communication. Second, pod can talk across node without NAT, whether they are on the same node or a different ones. Pods can communicate freely without any extra translation layer. This keeps the network simple and fast. Next, services expose your application. Kubernetes services give your app stable endpoint for both internal and external access, and also they handle load balancing out of the box. Next, DNS-based service discovery. Pods don't need to remember IP. They use the service names, making the system easier to scale, debug, and maintain. These 4 goals are the foundation of Kubernetes networking, helping your apps connect reliably, securely, and automatically. In Kubernetes, every pod gets a unique IP addresses inside the cluster. That means pod can talk to each other directly using their IPs, no need for port mapping or NAT. And when the pod has a multiple container, they all share the same network namespace that lets them communicate using localhost, just like process running on the same machine. For example, if container A runs a web server on port 80, container B in the same pod can reach it using curl localhost 80. That's simple and fast. On the left, you can see the architecture. Pod A talks to pod B using direct IP communication. Meanwhile, pod C has the 2 containers, a web server and a sidecar, both sharing the same localhost. Now, this IP-based model is powerful, but remembering all those IPs can be a tough, right? That's exactly where services and DNS comes in, and we'll talk about this next. So how does Kubernetes handle networking behind the scenes? It does not do it alone. It uses CNI plugins, short for Container Network Interface. These plugins handle the actual network setup on each node, allowing pod to talk to each other across the entire cluster, no matter which node they are on. Some popular CNI plugins include Flannel for simple overlays, Calico for policies and BGP, and Cilium, which use fast eBPF based routing. If you are using kubeadmin to set up your cluster, you will need to manually install CNI plugin using something like kubectl apply-f calico.yaml. But with managed services like EKS or GKE, the CNI is pre-configured for you. On the right, you can see how CNI handles routing between nodes, managing the communication, IP allocation, and even load balancing. The result, pod on node 1 can talk to pods on node 2 like magic, but it's just a great networking. Here is a big challenge in Kubernetes. What if pod crashes or restarts? Its IP address will likely change, breaking any existing connection. That's where Kubernetes services comes in to save the day. A services gives your app a stable front door with a fixed IP and the DNS name that never changes, no matter what happens behind the scene. It also acts as a load balancer, automatically distributing the traffic to a healthy pods only. Think of it like a hotel reception desk. Staff means pods might change, but the front desk means a service is always in the same place with the same phone number. A service acts like a permanent mailing address for your application. This ensures people can always find and use your application, even if the actual computers or pods running it are consistently changing, being replaced, or disappearing. In Kubernetes, services define how pods are accessed, whether it's for internal communication or exposing apps to the outside world. There are 4 main types: ClusterIP, NodePort, Load Balancer, ExternalName. Let's see one by one. ClusterIP, the default option for internal only access, great for backend and database communication. NodePort, expose your application on a static port of each node, handy for testing and development. Load Balancer, perfect for production. It gets a public IP and balances traffic across the pod. ExternalName maps your service to an external DNS name, useful for accessing managed service like external APIs. And a quick tip is use ClusterIP for microservices, NodePort for testing, Load Balancer for production application, and ExternalName when calling a service outside the cluster. Each type has its own role. The key is choosing the right one for your job. Now let's talk about the most commonly used service type in Kubernetes, that is ClusterIP. This is the default service type, which means if you don't mention any service type in your YAML file, Kubernetes will automatically create a ClusterIP service for you. So what does it do? ClusterIP creates a virtual IP, also called VIP, that can only be accessed inside the cluster. That means a traffic from outside the cluster cannot reach it. It's perfect for internal communication between the pods. For example, your front-end pods can talk to your backend pods using the backend ClusterIP service. Here is how it works. A request from the front-end goes to the backend service using the service name like backend.default.svc.cluster.local. That name gets resolved to the ClusterIP using Kubernetes DNS. Then kube proxy sends the request to one of the backend pods using load balancer. No need to worry about pods IP. Services handle everything behind the scene. It's simple, internal, and efficient, just what you need when the pod talks to each other inside the cluster. Now let's move on to the NodePort, the easiest way to access your app from outside the Kubernetes cluster. With NodePort, Kubernetes opens a specific static port on every node in a cluster. This port is usually picked from a special range 30,000 to 32,767. Once it's set up, user can access your application using any node IP address followed by the NodePort. Here is the pattern: HTTP node IP : NodePort. So even if your app is running deep inside the cluster, traffic from the internet can reach it using a NodePort on any node. This method is great for testing and development, on-premises setup, and when you don't want to use cloud load balancer. But keep in mind, it's not recommended for production. It offers limited flexibility and security. For example, you can run curl HTTP 192.168.1.10:30080 and it will forward the request to your app running on the port 8080 inside the pod. Simple, quick and perfect for small setup. Now let's look at the most powerful and cloud-friendly option, the load balancer service. This is the production grade solution for exposing your application to the internet, especially when you are using cloud provider like AWS, GCP or Azure. Here is what happens behind the scene. When you create a load balancer service, Kubernetes asks your cloud provider to automatically set up an external load balancer. It gives you a public IP address and routes the incoming traffic directly to your application running inside the cluster. It's completely auto-managed. You don't need to manually configure anything. This is perfect for real-world user, scalable web application, API that needs to be accessible from the outside. It also supports health checks, auto-scaling and high availability, making it ideal for the production. You can get the external IP by running kubectl get svc followed by the service name. In my case, it's my-service. So in short, load balancer is your go-to method when you are running application in the cloud and need reliable external access. Let's now talk about unique service type in Kubernetes, that is external name. Unlike the other service we have seen, external name does not actually route the traffic. Instead, it simply acts as a DNS alias, mapping a Kubernetes service name to the external domain. Here is why it is useful. Let's say your app inside the cluster need to connect to an external service like managed database, for example, AWS RDS, or a third-party APIs. Instead of hard-coding the external host name everywhere in your application, you can create an external name service in Kubernetes. This way, your application can just use a local name like external-db and Kubernetes will automatically resolve it to a something like db.example.com using DNS. This gives you no IP hard coding, cleaner service discovery and it's easy to update if the external address changes. Just define a simple YAML file like this. Type external name followed by the db.example.com. Then your app can connect using curl http:/external-db. Remember, there is no traffic routing, no load balancing, just pure DNS mapping. It's a lightweight, clean and perfect for integrating with external services. Now let's understand one of the most important behind the scene concept in Kubernetes endpoint. Every time you create a service in Kubernetes, it needs to know which pods to send a traffic to. That's where the endpoint comes in. Endpoints are simply a list of live pods that the service can route the traffic to. And the best part, you don't have to manage this list manually. Kubernetes automatically updates it in a real time. If a pod crashes or a new one starts, the endpoint list changes automatically. No manual effort needed. Now here is how traffic routing works. When someone sends a request to a service, Kubernetes forwards it to our endpoints and then picks one of the pod IPs from that list, usually using round-robin load balancing to send the traffic here. You can see this flow in the diagram with the arrows going from service to endpoints and from endpoints to a pod. This ensures only healthy pods receives the traffic. Failed pods are automatically removed and new pods are added as soon as they are ready. You can view the live list of endpoints using the command kubectl get endpoints and the service name. This shows you exactly which pod IPs and ports the service is routing to. In short, endpoints are dynamically bridged between the stable services and every changing pods, keeping everything running smoothly without your intervention. Do you know Kubernetes has built-in DNS? That means you do not need to memorize the pod IPs anymore. Every time you create a service, Kubernetes automatically creates a DNS record for it. So instead of calling your backend using an IP address, you can just use the service name like this, curl http -backend-service. Behind the scene, here is what happens. The front-end pod makes a request using the service name. Kubernetes DNS, usually core DNS, look up the name. It then resolves it to the cluster IP of the backend service and returns the IP address. That's called the DNS-based service discovery. The full DNS format is service-name namespace.svc.cluster.local. But in most cases, you only need the service name. Why this matters? Your app keeps working even if the pod scale or restart. It's auto-discovered and it's perfect for dynamic cloud native environment. When it comes to making your Kubernetes application accessible from outside the cluster, you have the three main options. First is NodePort. It exposes your service on a port on every node in the cluster. You access it using NodeIP:port. It's simple to set up but has a limited flexibility and is mostly used for the development. Second is load balancer. This is a production ready and used in cloud environments like AWS, GCP or Azure. It automatically provisions an external load balancer and assigns a public IP. Great for scalability and public access. The third most powerful is Ingress. Recommended for the production. It handles HTTP and HTTPS traffic using host names and path. It also supports advanced features like TLS termination, SSL cert management and custom domain. You can see a comparison. NodePort is a basic and good for development. Load balancer is ideal for simple cloud apps. Ingress gives you the best performance, flexibility and security. Key recommendation here is use Ingress for the secure and scalable access, especially when running multiple services behind the HTTPS. We are skipping the network policy since it's an advanced topic and also requires additional setups like CNI plugin. Don't worry, we will cover it in future advanced Kubernetes session. Let's look at a real-world example of how Kubernetes networking works using a three-tier architecture. Imagine you have a web application made up of three types of pod. Front-end handles the user interface, backend contains the business logic, database stores your data. The communication goals are simple. The front-end should connect to the backend and the backend should connect to a database and a user should access the application from their browser. Here is how networking flow works. The front-end pod talks to the backend using its service name, which resolves to the cluster IP. The backend pod connects to the database using the service name like db-service and the user hits to the front-end using the load balancer or a ingress. Network policies help secure this communication. Only the backend is allowed to talk to the database. All other direct access is blocked. This prevents misuse or attacks. This layer approach brings modularity, security and scalability, which is perfect for microservices based application. And the key takeaway is this is a real world pattern that enables the scalable microservices which secure and structure the communication inside the Kubernetes. Let's quickly recap everything you have learned about Kubernetes networking. Pod IP management. Each pod gets its own IP and container inside shares the local host. CNI plugin architecture. Tools like Calico or Flannel handles the networking across the node. Service stability. Service offers stable access and endpoints dynamically linked to the live pods. DNS Service Discovery. DNS make it easy to find a service by name instead of IP. External service access. You know how NodePort, load balancer or ingress expose the service to the outside world. Network security. Policies control the traffic flow to make your cluster secure. You have mastered pod communication, service management, external access and security policies. Skill acquired from this session is pod networking, CNI plugins, service types, DNS discovery, external access and network security. You are well on your way to becoming a Kubernetes networking expert. And the key takeaway is understanding the Kubernetes network help you to build a reliable, secure and scalable applications. Try applying this concept in your own cluster and explore more advanced topics like ISO service mesh and network policies. And that's it for this tutorial. You now have a solid understanding of how Kubernetes handles the networking from pod communication to exposing application externally. If you found this video helpful, don't forget to like, subscribe and hit the bell icon for more DevOps and Kubernetes tutorials. Stay tuned for the demo session on this topic. Thanks for watching.